Our IPD project titled Approximating Vector Database Hash Function Using Kolmogorov R1 Networks by Amod Joshi, Akash Ram, and Archie Patel. A vector database stores high-dimensional embeddings that represents the semantic meaning of data. It enables similarity search across image, text, audio, etc. It powers various applications like retrieval, augmented generation, recommendation system, and nearest neighbor search. Unlike traditional database, retrieval is based on meaning, not exact matches. Various applications of vector databases include medical imaging, industrial defect retrieval, forensic and security, wildlife, bioacoustic. Traditional pipelines rely heavy on non-interpretable black box model that often offer weak explanations. Feature extraction used with LSH often produce embeddings that are not human interpretable. Literature survey shows that interpretable hashing remains unexplored. So there is a need for interpretability when it comes to trust, debugging, regulation, and bias mitigation. There are various limitations of traditional model. Classic models, they are very rigid. They are very close to it. So when there are new entries, you need to do training again and again. They don't support even exploratory and open source queries. Poor transparency in what feature embedding represent.
Our approach. Our approach is a Siamese network that takes into account one anchor, one positive, and multiple negatives. Then we use k-triplet loss to train the model. So k-triplet loss is a generalized form of triplet loss. In triplet loss, we have one anchor, one positive, and one negative, where we try to learn embeddings of feature vectors, where the anchor and the positive embedded closer together, and the anchor and the negative embedded far away from each other. K-triplet loss takes into account multiple negatives, so the anchor and the positive are embedded closer together, whereas the anchor and all the negatives are embedded farther away from each other. What is KN? KN is a neural network architecture where instead of learning weights and biases, it learns activation functions on each node. Next.
Before showing the result, I will show first the demo of our model. Here, you have to first give an index to the model. Let's say we pass the index 2. The model will fetch the index 2 from the vector database and it will show the top k similar results of that index. Here the k is defaulted to number 5. Okay, here now you can see we have got 5 similar ones as opposed to the query result. After this, we get a generalized heat map of the image 1. Here we can see the overall how the model is thinking. The number 1 is represented. Here you can see the model has accurately captured the shape of number 1. The green and yellow regions are the regions of highest activations, whereas the purple is the region of the lowest activation. These next 5 feature maps will be the individual top feature maps of the model. This is the feature map of the feature 4 of the model. Here we can see what the feature 4 of the model has captured. Here the feature 7, feature 21, feature 8, and feature 14. Now coming back to the results. Here we have compared the triplet loss and the k-tuplet loss. On the left hand side, we can see the comparison between the loss value and number of the training epochs. The yellow curve is the curve of the k-tuplet loss. The red curve is the curve of the triplet loss. From this, we can see that the k-tuplet loss has a more stable learning curve and faster initial convergence than the triplet loss. On the right hand side, we have the performance gap analysis, which basically tells during every epoch which loss was superior. From the graph, it is very obvious that k-tuplet loss was always superior in every epoch. Next, we have compared our model to other benchmarks in the deep learning hash-based models. We have compared it to other 4 models. On the left-hand side, we can see the precision recall curves of all the models and our model. Our model is the green line or the green curve. We can see we have not lost any computational power or the accuracy. We have not lost anything, and also we are given the interpretability. On the right hand side, we can see the map or mean average precision of our model and other models. Here also, it is very clear that we have got the results as compared to other model, plus we're also providing the interpretability. Next, we are showing the transfer learning capabilities of our model. The orange curve is our model, which was trained from scratch, and the green one is a pre-trained model. The pre-trained model here is the feature extractor. Here we have used the resonate. From this, we can see the pre-trained model and our scratch model both performs on the same level, which means our model is also transfer learning capable. Thank you so much.
आमोद
बोल ना।
आमोद ये लास्ट इमेज में चेंज करने बोला था ना, देखो बहुत बहुत
अरे
सस्पिशियस लग रहा है।
हाँ हाँ रुक में फिर इसमें चेंज कर सकते हैं, क्या बोलते हैं, ड्यूरिंग दैट प्रेजेंटेशन के टाइम चेंज कर दो, नहीं तो रुक चेंज कर दूं।
कर दे
इसमें नहीं आकर उसमें करते हैं, कल दिखाने का ना उसमें।
अरे ये अगर
कर
समझ
देते हैं।
जूनियर को दिखाया, जूनियर बोला ये क्या किया है लोग ने।
कौन किसको? अरे
लाइक
जूनियर का
मैं क्या बोल रहा
अगर
हूँ,
जूनियर का छोड़ रहा है।
सुन ना, सुन सुन सुन